Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're evaluating deflections using the superposition method with the assistance of beam tables. The next example that we'll look at is a simply supported beam with a point load at B and a distributed load between D and E. I'll give a quick sketch of the deflected shape of that beam. We're asked to evaluate theta A, which is the rotation at A. It's that rotation there. V sub C, the deflection at C, the midpoint of the beam, which I'll call V sub C. And V sub D, the deflection at D, which is located right there. Okay, we'll start with V sub C, deflection at the midpoint. We're going to break this into two load cases. The first one is going to be the deflection due to the point load, 20 kip. Sketch the deflected shape. The deflection at midpoint I'm going to label as VC1. This is case 1. Case 2 is going to be the deflection due to the distributed load. Distributed load acting over the end of the beam, 5 kips per feet. I will sketch that deflection and label deflection at the midpoint VC2. The superposition principle tells me that the total deflection VC is the sum of VC1 plus VC2. So I'm going to evaluate these separately. Starting with case 1, VC1, we'll refer to the beam tables. We have a point load not located in the center of the beam, so the applicable load case is this one right here. Okay, now look at our deflection. We can evaluate deflection at A. That's not what we want. The general equation is valid from 0 less than or equal to x less than or equal to A. That's this region of the beam. Okay, if we go back, we actually want the deflection on the other side of the load. So what we're going to have to do is switch the coordinate system, start x at this end, call the distance, this distance A and this distance B. So let me go ahead and label that so far. This distance right here will be A, equal to 9 feet, and this distance right here will be B, equal to 3 feet. All I did was swap the coordinate system, defining x coordinate system from the left end of the beam. Okay, now look at the equation. V equals negative PBX over 6LEI times L squared minus B squared minus X squared. Let me copy that down. VC1 equals negative PBX over 6LEI times L squared minus B squared minus X squared. We already said B is equal to 3 feet. L is the length of the beam, 12 feet. And x is going to be the distance from the left end to the point where I'm evaluating deflection. That's the midpoint of the beam, so x equals 6 feet, half the length of the beam. X equals 6 feet, okay? Now notice I have EI in kip inches squared, everything else in feet, kip feet. So for now, I think I'm going to evaluate this equation and leave EI symbolic. It will be a little bit easier if I do that. Plug everything else in. P equal to 20 kips, B equal to 3 feet, X equal to 6 feet, times L squared, 12 squared, minus B 3 squared, minus X 6 squared, and that whole thing has units of feet squared, divided by 6 times L, 12 feet, over EI, okay? And that all the numbers in there compute to negative 495. This is over EI, and the units are, we have a kip, feet to the 4th on the top, over feet on the bottom, so kip feet cubed. And what I'm going to do here is convert to inches. I think that's the easiest thing to do by multiplying by 12 cubed inches cubed. Okay, and then I'll go ahead and substitute in my EI, 1.2 E6 kip inches squared, and the whole thing, so I've kip inches cubed on top, kip inches squared on the bottom. Whole thing reduces to inches, and the value is negative 0.713 inches. Okay, that's our value for VC1. Now let's look at VC2. Which load case do we want? We want a distributed load acting over the part of the beam. Okay, so this is the load case we want right here. We can evaluate deflection directly at the transition, but that's not what we want here. So notice there's two equations, one for x less than a and one for x greater than a. Again, the situation is going to be that we want to evaluate a deflection over here in the free part of the beam, which the way it's drawn here is x greater than a. So we want this equation right here. However, again, because our load is on the other side of the beam, we're going to have to switch the coordinate system, define x going from the left end. Okay, and so this distance right here would be a equal to 4 feet, and this distance over here would be b equal to 8 feet. Okay, so if I go, let's just take a quick look at that equation right now. It's very complicated, but I'll go ahead and come back and sketch it down. Everything is in terms of a, l, and x, and that would be VC2 equals negative w a squared over 24 l ei times, I hope I can fit it all in here, 2x cubed minus 6lx squared plus a squared x plus 4l squared x minus a squared l. Okay, and when you're doing these calculations, you need to be very careful. Best to use a program, a MathCAD. Just punching these numbers into your calculator. Be very careful because it's very easy to make mistakes. Okay, so what am I going to use here? Again, I'm going to use a equal to 4 feet. I'm going to use L equal to 12 feet, and I'm going to use X. It's from the right end of the beam over to where I want to evaluate the load. That's the midpoint. X is equal to 6 feet, and I'm going to leave the EI symbolic until the end. So I have negative 5 kips per feet times a squared 4 feet squared divided by 24 times 12 feet. Carry the EI along, excuse me. Then, and all of these numbers have the same units, so I'll leave them out. 2 times 6 cubed minus 6 times 12 times 6 squared plus 4 squared times 6 plus 4 times 12 squared times 6 minus 4 squared times 12. Okay, this whole thing in here, units of feet cubed. So the number is negative 333.3, and the units again are going to be, what do we have, kip per feet times feet squared. So kip feet divided by feet, that's kip, and then over here feet cubed. Again, we have kip feet cubed over EI. This time I'll go ahead and write it in, 1.2 E6 kip inches squared. To get the top into inches, I'm going to multiply by 12 cubed inches cubed, and that number is negative 0.48 inches. That's VC2. Okay, so to summarize, the total deflection, VC1, negative 0.713 inches, and VC2, negative 0.48 inches. Add them together and you get VC equal to negative 1.193 inches. Okay, what is our sanity check? The units checked out, and I was very careful with units. The contribution from the two loads is about the same order, which makes sense, as they're both the same magnitude. And the overall deflection is around an inch. This is a reasonably small number. Everything seems to add up. We'll go ahead and continue with the other two in the next video.